Imagine for a moment that everything you see and experience, the stars glittering in the night sky, the warmth of sunlight on your skin, the swirl of galaxies, and even your own sense of self, is not quite as it appears. That reality, in all its complexity and grandeur, might just be a kind of projection, a three-dimensional illusion arising from information stored on a distant two-dimensional surface. This is the heart of the mind-bending concept known as the holographic universe. To understand what this means, let's start with the idea of a hologram. In everyday life, a hologram is a three-dimensional image created by shining a laser onto a specially prepared two-dimensional surface. The information for the entire 3D image is encoded on this flat surface, so that from different angles, the image appears realistic, almost as if you could reach out and touch it. The holographic principle takes this analogy and applies it to the fabric of the universe itself. The roots of the holographic universe concept go back to the 1970s and 80s, when physicists began grappling with the mysteries of black holes. Stephen Hawking, Jacob Bekenstein, and Gerard T. Hooft, among others, made a startling discovery. The amount of information, or entropy, that could be stored inside a black hole was not proportional to its volume, as you might expect, but rather to the surface area of its event horizon, the boundary beyond which nothing can escape. In other words, all the information about what falls into a black hole seems to be encoded not inside it, but on its surface. Leonard Susskind and Gerard T. Hooft took this idea further, proposing that perhaps the entire universe works like this. The holographic principle suggests that all the information contained within a volume of space can be described by information encoded on its boundary. This means that our three-dimensional reality may, in some sense, emerge from physics happening on a two-dimensional surface at the edge of the universe. But how could this possibly be true? To answer that, we need to explore the strange world of quantum gravity, a realm where the rules of quantum mechanics and general relativity collide. In quantum mechanics, information is fundamental. In general relativity, space and time bend and stretch in response to matter and energy. When you combine the two, as in the extreme environment of a black hole, contradictions arise. For instance, if you throw something into a black hole, does its information get lost forever, violating quantum theory? Or is it somehow preserved, as the holographic principle suggests, on the surface of the black hole itself? In the late 1990s, physicist Juan Maldacena made a breakthrough. He showed that a certain kind of universe, a five-dimensional space with gravity called anti-de Sitter space, could be mathematically equivalent to a four-dimensional universe without gravity living on its boundary. This relationship is known as the ADS-CFT correspondence, and it provides a concrete realization of the holographic principle. In Maldacena's framework, the physics inside the bulk of the universe can be fully described by a theory living on the boundary, with no gravity at all. In a sense, the real action happens on the boundary, and our familiar three-dimensional world is a kind of projection, like the image in a hologram. While our universe isn't exactly the kind described in Maldacena's work, it isn't anti-de Sitter space, and it has a positive cosmological constant. The correspondence offers tantalizing hints that the holographic principle may be a deep and general feature of nature. If the universe is truly holographic, what does that mean for us? For starters, it challenges our most basic intuitions about space, time, and reality. The world may appear three-dimensional, but the fundamental description could be two-dimensional. Just as a hologram can look fully three-dimensional even though it's encoded on a flat surface, so might our universe emerge from information imprinted on a cosmic boundary. This perspective could solve some of the most perplexing puzzles in physics. Take the black hole information paradox. If information is stored on the event horizon, it need not be lost when the black hole evaporates, preserving the laws of quantum mechanics. The holographic principle also offers new ways to approach the problem of quantum gravity, suggesting that gravity itself may be an emergent phenomenon, arising from more fundamental quantum processes on a lower dimensional surface. The implications don't stop at physics. Philosophically, the holographic universe forces us to reconsider the nature of reality itself. Are we, in some sense, shadows projected from a deeper, more fundamental level of existence? Is our sense of space and depth an elaborate illusion stitched together from information on a distant screen? Of course, these ideas are still speculative. The holographic principle, while supported by compelling mathematical evidence in certain contexts, has yet to be confirmed in experiments. Physicists are searching for observable consequences of the principle, subtle signatures in the cosmic microwave background, or hints in the behavior of subatomic particles that might reveal the universe's underlying holographic nature. Yet, even as a theoretical framework, the holographic universe has already transformed the way we think about the cosmos. It has inspired new lines of inquiry into the fabric of space-time, the nature of information, and the unity of the laws of physics. In the end, the holographic universe isn't just a wild idea from the edges of theoretical physics. It's a testament to the power of imagination and mathematics to probe the deepest mysteries of existence. Whether or not it turns out to be the final answer, it challenges us to look beyond the surface of things, to question our assumptions, and to wonder what reality might be like if we could see it from a higher vantage point. So next time you gaze up at the stars, remember, what you see may be just a shimmering projection, a cosmic hologram, whispering secrets from the edge of the universe. The true nature of reality may be far stranger and far more wondrous than we ever imagined.